Imagine you're standing in an empty, square bedroom. Hovering right in the middle is a glowing orb. Now imagine trying to tell a blindfolded friend exactly how to reach out and grab it. You can't say, "walk over there," or "reach up a bit." Those words mean entirely different things depending on where your friend is standing. You need a universal set of instructions. We usually start on the floor. If the room is a grid, you could tell them to walk 3 steps forward along one wall and 4 steps right along the other. That gets them standing right underneath the target. This diagram shows 2 distinct points. The left side plots a point flat on a plane using just 2 numbers. But to reach our orb, as the right side shows, requires a 3rd number to represent lifting off that grid and into the air. Flat math systems only work for flat surfaces. To map a physical reality, we have to introduce a specific dimension for height. That vertical height is what mathematicians call the z-axis. It is simply the measurement straight up from the floor. This system works perfectly for navigating a room shaped like a rigid box. But what happens if the space you need to measure doesn't have straight walls or right angles? Imagine the square walls of our room dissolve and curve into a tall circular silo. The orb is still in the exact same spot, but our straight grid lines don't fit against these curved walls anymore. Instead of measuring along a flat wall, we map the floor differently. We start at the center, measure the straight line distance out toward the edge, the radius, and then sweep that line around like a radar until it points directly under the orb. That sweep gives us an angle. Once we have the radius and the angle pinned down on the floor, we simply shoot a straight line up to reach the exact height of the target. This is the cylindrical coordinate system. It is the natural choice anytime you need to map fluid flowing through a pipe, current moving down a wire, or forces on a spinning wheel. By swapping rigid intersecting planes for a radius and an angle, we adapted our math to perfectly match a curved cylindrical environment. Now, let's remove the walls and floor entirely. The silo vanishes completely, leaving our orb floating in an endless, empty void. There is no up, no down, and 0 flat surfaces to measure against. To find the orb here, we use the spherical coordinate system. Imagine floating at a central origin point in the dark, pointing a laser straight above your head. First, you tilt the laser downward by a specific angle to match the target's elevation. Then you spin horizontally, a second distinct angle, until the beam is perfectly aligned with the orb. Finally, you extend the beam a precise radial distance along that path until it hits the center. 2 angles and 1 distance.